Good morning, pre-calc students. Today we're going to finish section 2 of chapter 7. It's not a very long section, and I realized that the next thing I had was for you to do some problems on your own. So I'm going to do a quick review of what we learned yesterday. We talked about sectors of circle is the region of a circle bounded by a central angle and its intercepted arc. Arc length is how long the sector is. So if we have a circle and we have a central angle, the arc length would be the length of this part of the circle. The area would be the space inside the actual sector. So we call arc length S, and in radians, the arc length is S equals r theta. So S equals radius times the measure of the angle. And the area is given by capital K. The area is half times the radius squared times theta, which could also be written in terms of arc length. So the area is half times the radius times the arc length. If you're measuring in degrees, then we take these formulas for radians and we multiply them times the conversion factor of 2 pi over 360, which I had written down here, 2 pi over 360. So we have the radius times theta times 2 pi over 360, which when simplified gives us this, that the arc length equals pi r theta over 180. And then the area of the circle is, the area of the sector is the area of the circle times the fraction of the circle that it is. It's the angle divided by 360. So if we write that in an easier way to see, K equals pi r squared theta over 360 degrees. Those are the formulas we'll be using today. We went through example 1A yesterday, but I'm going to go through it again so that you can refresh your memories. We need to find the arc length and area of a sector whose central angle is 60 degrees with a radius of 12 inches. So 12 inches, I can't write very clearly with this. Let's try this. 12 inches and 60 degrees. Arc length is, to refresh our memories, radius times theta. That's in radians, but we want it in degrees. So we're going to do pi r theta over 180 degrees, which is the formula that we had right here. So pi r theta over 180 degrees, in this situation, we can keep working with pi. The radius is 12. Theta is 60 degrees. All of this over 180 degrees. You should be able to see right away that 60 and 180 have a common factor. So this becomes 12 pi over 3. And then 3 can divide into 12, so it's just 4 pi. And we are measuring in inches. This is a length, it's arc length, so 4 pi inches. If you can write your answer in terms of pi so that it's a nice, neat thing like this, do it. Sometimes it won't be, sometimes you'll have decimals, and then you can round it to the nearest hundredth or thousandth or tenth. Alright, area, we said, is going to be the area of the circle, pi r squared, times theta divided by 360 degrees. So that means that the area will be pi times 12 squared times 60 degrees, all over 360 degrees. You should be able to see that 60 can divide into 360 and we'll get pi times 144, because that's 12 squared, over 6. And then 144 divided by 6. Actually, it would be easier if we left this up here as 12 times 12. Because now we can see that 6 divides into one of these 12 two times. So 2 times 12 is 24, and 24 times pi. And we are measuring area, so it's going to be 24 pi inches squared is the area for that sector. Alright, the next example is from your book, and since many of you might not have your books with you, I have written it here. It's page 263, example 1. A sector of a circle has arc length 6 centimeters and area of 75 centimeters squared. Find its radius and the measure of its central angle. We are not given degrees, or we're not told to find degrees or radians, so we get to choose. The formula for radians is easier, so let's use that one. Arc length equals radius times theta. We know that the radius, we actually don't know the radius, we need to find the radius, but we know that the arc length is 6 centimeters. So 6 equals the radius times the central angle, but we don't know what that is yet. What can we do? We do know the area, and we know that area, K, equals half times the radius times the arc length. So we can use this to find the radius, because we know the area is 75, we know that it's half times the radius, and we know the arc length is 6. So it's going to be 75 equals 3r, so that means that the radius will be 25. We're measuring in centimeters, so the radius is 25 centimeters. And we can take that and put it back in over here to our formula, that 6 equals 25 theta. If we divide both sides by 25, we get 6/25 equals theta. And if we are measuring in radians, we can leave it as that. Theta equals 6/25 radians. If we were measuring in degrees, we would need to use the other formula, but we're going to leave this one as radians. We could change it to a decimal if we want. We could say that theta is approximately equal to 0.24 radians. I would accept either unless I specifically tell you to give an exact or to round it to a particular place. Alright, so these 3 problems I want you to do on your own. And I'll give you a chance to fill them in, to write them, submit the answers so I can see if you understood it or not. We can also go over these on Friday if you have questions. Alright, the answers that you should have gotten are, for number 1, that the arc length is 1.8 pi centimeters, and the area is 7.29 pi centimeters squared. For 2, the arc length is 4 pi miles, and the area is 6 pi miles squared. And for 3, apparently I don't have the answer already prepped, so we'll do that one together. Find the measure in degrees and radians of the central angle of a sector whose arc length is 31.4 feet, so S is 31.4 feet, and whose area is 157 feet squared. Well, we just did an example like this, so we know we have to find area first. Area equals half times the radius times the arc length. So 157 equals half times the radius times 31.4 feet. So that means 157 equals 15.7 r. And when you divide 157 by 15.7, you get 10. So the radius is 10 feet. We don't need to know the radius specifically, but we need it for finding the central angle. So we can take this and put it back into arc length, which is r times theta. So the arc length is 31.4. We don't know r, but we do know that, we do know r now. We don't know theta. We know that r is 10, and we need to find theta. When you divide by 10, you get 3.14 is theta. 3.14 you should recognize as being pi. So our answer in degrees will be very close to 180. But we have not been given exactly pi, so we're going to work with it this way. But in radians, theta is 3.14. In degrees, what we could do is we could take the arc length, which is 31.4, and use the other formula that is pi r, which is 10, theta, which we don't know, over 180. Now 110 and 180 can cancel out, so we're going to do 18 times 31.4, which is 565.2, equals pi times theta, and then we need to divide by pi. When you divide by pi, preferably using the pi button on your calculator, you will get 179.91 degrees. Like I said, it is very close to 180. You could even round it to 180. So the answer is that theta equals exactly 3.14 radians, and theta is approximately 179.91 degrees. That's the answer for the third part of the triad. Alright, the last thing we're doing is learning about apparent size. This is also from your book, so I have the excerpt from your book here. I will read it out loud because I would have someone read it out loud in class. Apparent size. When there is nothing in our field of vision against which to judge the size of an object, we perceive the object to be smaller when it is farther away. For example, the sun is much larger than the moon, but we perceive the sun to be about the same size as the moon because the sun is so much farther from Earth. Thus, how big an object looks depends not only on its size, but also on the angle that it subtends at our eyes. The measure of this angle is called the object's apparent size. So, the apparent size of an object is referring to this angle right here. And we have example 2. Jupiter has an apparent size of 0.01 degrees when it is 8 times 10 to the 8th kilometers from Earth. Find the approximate diameter of Jupiter. And they tell us that we can do this by drawing a diagram, an exaggerated diagram, where we've got Jupiter out here, and we're over here looking at it, and the angle formed by the top and the bottom of Jupiter, and the diameter of Jupiter would be here, which is approximately the arc length of this giant circle that goes like that. So they tell us in the solution, as the exaggerated diagram above indicates, the diameter of Jupiter is approximately the same as the arc length of a sector with central angle 0.01. And we're measuring in degrees for this central angle, so we need the degrees formula. So arc length equals pi r theta over 180 degrees. Now you'll notice that the book uses theta divided by 360, theta divided by 360 times 2 pi times the radius. But you can also use this formula also. I find this formula to be easier, so we'll work through it with that. So if the arc length, we want to find the arc length because that will be the diameter, so we'll change this to diameter. It's pi times the radius of this circle would be the distance to Jupiter. So 8 times 10 to the 8th times theta, which is 0.01. All of that divided by 180 degrees. And when you multiply all of that out, you get approximately 140,000 kilometers. All right, I know that probably has confused some of you, so we'll do a couple more examples with that. These are not in your book. So example 2b, you are in London and see a tour bus 100 meters away. The apparent size of the bus is 1.44 degrees. Approximately how tall is the bus? Pictures are very helpful for these kinds of things. So if we have our bus, and we have us over here, and you're looking at the bus, top and the bottom of the bus, and that angle, we're told, is 1.44 degrees because the apparent size, remember, is the angle formed by the top and the bottom of the object. We're also told that it's 100 meters away, which is approximately the radius. And we want to know how tall is the bus. So again, we're looking for this right here, the arc length. So we're measuring in degrees, so we'll use the same formula as last time. Arc length equals pi times the radius times theta, all over 180 degrees. So pi times 100 times 1.44 divided by 180 degrees equals 2.51 meters. Now, if you got an answer slightly different than that, or if you did 3.14 for pi instead of using the pi button, you will get an answer that is slightly different. You should use the pi button as much as possible. You would have gotten 2.512. Use the pi button if you can. You can write down rounded answers as part of your work, but use the full answer. Use the exact answer until you get to the very end. Do the rounding for the final answer at the very end. So our answer for part A is 2.51 meters. Example 2c says, what is the apparent size of the bus in degrees if it is only 40 meters away from you? Include 3 significant digits in your answer. So we're using the same bus, so the height of the bus is 2.51, which we just figured out. We want to know the apparent size. That's going to be theta. And our distance this time is 40 meters. Again, a diagram could be helpful. We have our bus, which looks a little bigger because it's closer. We have us right here, looking at the bus. We want to know what is theta if we're only 40 meters away now, and the bus is 2.51 meters tall. We can use radians or degrees for this. Again, the formula for radians is easier, so we can use that. Arc length equals the radius times theta. We know that the arc length is the height of the bus, so it's 2.51, and the radius is 40, and we want to know theta. So we do 2.51 divided by, and I can't get my calculator to work, 2.51 divided by 40, which is 0.06275. That's theta, but we're told 3 significant digits in the answer. So that would be 0.0628 equals theta. Remember, significant digits, the zeros at the beginning don't count. Alright, since we understand things in degrees better, let's go through this really quickly in degrees also. So we would use the arc length equals pi r theta over 180. So we have 2.5 equals pi times 40 times theta over 180. And then we'd multiply times 180. And we'd divide by 40 pi. And that will give us theta. And when we multiply that out on our calculators, we get that theta is approximately equal to 3.5953, except that we can only have 3 significant digits, so this rounds to 3.60 degrees is approximately equal to theta. And we have to keep that 0 because of significant digits. There's a 0 here because the next digit after the 9 is 5, which means 9 rounds up to 10. So it becomes 3.6, but we need 3 significant digits, so we have to include that 0. Alright, that is the end of the lesson. These are the problems that you need to know how to do for homework. If you don't have your books, I have posted that page in Google Classroom. You also get access to all of the answers, so you can know right away if you are correct. You should work on you should work on some of them to make sure you understand, and come with your questions on Friday. I will be able to see if you have watched this entire video, and I'll see your answers from the Try It problem. Now, some of you probably are wondering how to get the answers to those Try It problems. So if you got the Try It questions correct, you can stop watching the video right now. If you got them incorrect and you would like to know how to do them, I'll go over that right now for you. Let me minimize this. And okay, so the first one, we're given the arc length. We need to find the arc length and the area of a sector, where the central angle is 40 degrees and the radius is 8.1. Give the answers in terms of pi. We are dealing with degrees, so we need the formula arc length equals pi r theta over 180. And we need area equals pi r squared theta over 360 degrees. And then we just fill in the information. We know that the radius is 8.1, so it's pi times 8.1 times theta, which is 40 degrees, all over 180. I'm going to move this, oops, not that. I'm going to move this up here for right now. And we can simplify this, divide out 20, and we end up with 2 and 9 down here. So we have 2 times 8.1 times pi divided by 9. And then if we do all of that, 2 times 8.1 divided by 9, we get 1.8 exactly. So 1.8 pi, and we're measuring in centimeters, so that's the arc length. Follow a similar procedure for the area. I'll see if I can work through it up here if I have enough room. We know that pi is still pi. The radius is 8.1, so it's 8.1 squared times 40 degrees over 360 degrees. These will simplify. This becomes a 9 on the bottom. So it becomes 8.1 squared, which is 65.61 pi divided by 9. And when you divide that, you get exactly 7.29. And then we still have pi. And it's area, so it's centimeters squared. Alright, the second one is the exact same thing, except this time it's in radians instead of degrees. So the arc length is a little easier. Arc length equals radius times theta. We are told that the radius is 3, and the central angle is 4 pi over 3. So the 3's will cancel out, and we are left with just 4 pi, and we're measuring in miles, so 4 pi miles. You could find that in decimals, but because it gives us such a nice clean answer like 4 pi, we'll leave it like that. And then area equals half times the radius, and since we know the arc length, and since it's such a nice number, we'll use half times the radius times the arc length. So it's half times 3 times 4 pi. And we'll get 3/2 times 4 pi. The 2 and the 4 cancel, and we end up with 6 pi. And we're measuring area, so it's miles squared. And that's how you do the two try-it problems.